So good morning and good evening, everyone. Thank you for joining this seminar on bio-inspired robotics, the nature meets technology. And I'm Dr. Tingjun Lei, assistant professor from the School of Electrical Engineering and Computer Science from University of North Dakota. And today my topic is the bio-inspired cognitive map model for autonomous robot navigation and exploration. And this is the research is grounded in the biologically inspired models and aims to bridge the gap between the neuroscience and the robot navigations. And this research is collaborated with the Matt Hicks, Dr. Raw, Dr. Cruz, and Dr. B. So first, just as usual, we talk about the motivation and background why we do this research. So the concept of the cognitive maps was originally proposed in psychology to explain how animals, particularly the mammals, form mental representations of space to navigate their environments. Inspired by this, researchers have long sought to develop artificial models that replicate these capabilities for autonomous robots. However, most existing robotic systems either require exhaustive exploration of their environments or lack like the biological possible structures. Our goal is to create a more efficient biologically realistic navigation systems that mimics the mammalian strategies. And the traditional robotics navigation often relies on complete environment mapping before planning. This can be inefficient and unrealistic in time-sensitive or unknown environments. And in contrast, biological systems use motivation and goals to navigate effectively, often without full knowledge of their surroundings areas. In our models, GDCMs or like Go Direct Cognitive Map emulates this bio-inspired approach, prioritizing purpose for like, navigation over exhaustive explorations. Our GDCM model is grounded in neuroscience. It incorporates five types of neurons discovered in mammalian's brain as the head direction cells, boundary vector cells, speed cells, grid cells, and place cells. These cells interact to form spatial representations and guide navigation. Unlike error models that may only use a subset of these, like they only use the grid cells or the place cells, our GDCM's model integrates all five neurons, reflecting their neural methods, roles, and interconnections. And prior to developing the GDCM, a hand of the cognitive map-based navigation and path planning algorithms were reviewed to ensure like originality and for comparisons. And we say the difference between GDCMs and other cognitive map models, we can list for several different categories. First, we think about the total environment exploration versus the reward-driven. Let's say the most like the cognitive map review to date use some kind of the complete exploration to learn the environment. Once learned, algorithms were executed to find the shortest path, usually during a post-processing steps, but occasionally concurrently. The exploration phase itself can be time-consuming. We all know that. And however, the GDCMs use motivation or goal to direct its learning and understanding of the environment. And this figure visualizes how minimal the GDCMs between a foraging or exploration method is shown in A, and we have the reward-driven approach in B. The AS, we have the much larger, like more nodes and segments covering almost entirely the empty space of the map. And in B is we have the smaller explorations. For path planning and graph search algorithms, the smaller the cognitive map, the networks are faster to resolve paths. The GDCMs only creates the necessary graph segments in a fraction of the time requirement required by the foraging or exploration methods. And the other, we can have the usage of the various the CM models. such as existing models vary in their usage of known cells, either only incorporating one of the cells, like the place cells, up to any combination of known cells. Or we have the configuration of the cells, such as whether a certain cell exists upstreams or downstream to a cell, or like certain cells contribute to another cell's firing. And also we have additional concepts extrapolated and added to the CM models to address memory, path planning, and navigation. Our model also embeds psychological strategies seen in animals, like the taxon navigation use cues and landmarks, like the praxis navigation repeats learned motions, and local navigation allows goal seeking from unfamiliar positions, and random navigation enables moments when cues are absent. So these four strategies are naturally integrated into our GDCM logic, providing the flexibility and the resilience in various environments. And the result of this architecture is visualized in this figure. I can begin in this yellow block initializing variables and the workspace and begin iterations. Determines the preferred directions, calculate the angles, distance to border, and integrate the speed. We have the speed cells over here and calculate the grid cells. If like not a goal, continuously advance robot and repeat. If at the goals, determine if initial iterations or if the iteration is not within 5% of the previous iteration steps, means okay, we have almost hit the best road. If so, to perform another training iterations. So we train this place cells and generate map. Finally, it calculates the RAM path planning algorithms of choice, and in case of the shortest path algorithms on the cognitive maps. The HDC means the head direction cells, and BVC means the boundary vector cells here. And the GDCM's models constructs like layered cognitive architectures. Navigation begins with the head direction cells estimating let's say the preferred directions. Boundary vectors and the speed cells influence the grid cell activities, which then models the place the cell fires. Place cells with higher activities from the graph nodes creating a cognitive map. And importantly, this map is formed during the navigations, not through the prior like exhaustive exploration, leading to the faster and more efficient path planning. And here's a little bit details about our different five cells in our proposed methods. The head directions cells functions like an internal compass, encoding the robot's orientation relative to its goal. When facing an obstacles, the cell rotates its preferred directions until a clear path is found. The research indicates that the grid cells firing is affected by the head directions. Preferred directions, or PD, is defined as like at every head direction cell location, the vectors that guides an actor closer towards the goals. Like any neural network, the HDCs can change over learning iterations. The default head direction cells PD is initialized as the unobstructed angle to the goal from the cell's location. And we are using some Gaussian process to define that preferred directions. And here has the figure illustrates the actor at the head direction cells whose initial like PD vector is pointing to an obstacle, as you can see here. The actor will randomly rotate until the PD is obstructed and advance until it can clear the obstacles. When the robot reaches an obstacle, like in A, while moving towards the target, like the green circle is like the target here, it will begin random like the counterclockwise or clockwise rotation in 45 degrees intervals until it's no longer obstructed. The figure shows a random selections to rotate like counterclockwise or the clockwise. And in B is the robot rotates 45 degrees clockwise, at which point the robot is still blocked. So in C, you can see the robot rotates once more and no longer object. So the PD updates towards directions that is not blocked. Um, and here is the a more detailed in the figures. The figures demonstrates the multi-scenarios of the head direction cells, preferred directions using the principal set force and explained in the previous slides. The first, like the A, is pretty simple, like straightforward scenarios where the preferred direction of the average head direction cells is directly towards the target. And B is to visualize how the random rotations can result into two different paths. And then C is in local minima situations, find the preferred directions after the first iterations. And this is the head direction cells for vector-based navigation. It will generate the vector kind of directions for the robots to move. And then we have the boundary vector cells. The boundary vector cells detect the proximity and directions to nearby obstacles. These form repulsive force, preventing the collisions and steering the robot around obstacles. Together with the head direction cells, they provide the real-time spatial awareness. So you can see that there's another, this is the local minima examples. It will get different type of the neural activities from the boundary vector cells. And they would prevent the just, hitting the walls and also knowing, okay, there's some boundaries over here, like this obstacle over here. And then we're using some angles and how to they have the neural activities to help to update it. And the head direction cells, they don't have the neural activities, by the way. And then it's the speed cells. The speed cells help the robot moderate its velocities. And while a robot attempts to find its way through an unknown environment, it may move back and forth, right? And move out of the local minima, evacuate like dead ends, or navigate a series of tight corners. These type of the movements do not allow the robot to accelerate and accumulate like high velocities. However, if traveling in a straight line for time, the robot may accelerate and achieve much faster speeds. This permits the speed cells. Therefore, the speed cell algorithm is straightforward. If the current preferred directions vector is within the predetermined threshold of the previous cells of the PD, the speed will increase. If not, the speed decreases. That means if the robot maintains a steady heading, its speed increases and reinforcing the efficient motion. And sharp turns and backtracking reduce speed, preventing unnecessary explorations. So this is like two different scenarios. One is pretty straightforward. It's going straight to the target. It can speed up. And when there's like ops over here, it have the sharp turning. So we will just decrease speed to prevent unnecessary explorations. And then it's the grid cells and place cells. The grid cells integrate directions. We have the head direction cells, right? We have the speed cells, and the obstacles approximate the boundary cells to provide the robust representations of locations. And the final values of the grid cells weight is combination of the boundary vector and speed cells activities, where the boundary vector cells at BVC are following the accounts for the head directions as well. And the place cells is here, the purple one, cells aggregate information from the neighborhood neighboring the grid cells to form the stable map nodes. These nodes are the building blocks of the final cognitive maps. Um, so as the robot navigates, here's the cognitive map construction process. Each layer updates. You see, direction vectors are recalculated, speed is integrated, and the spatial obstacles are mapped. When sufficient grid cells activity is presented, a place cell fires and is added to the cognitive map. This iterative process continues until the robots reach its goal. And the cognitive map model showing this is a sample environment with local minima obstacles and the start. This is starting point, this goal point. And starting with the beer workspace on the far left, the gray shaped object is the obstacles um, and using the aforementioned navigation strategies and logic. The first is the head direction cells, right? The HDC layer is trained with preferred direction vectors. These fit into the BVC, the board, um, is- and with the preferred directions in relation to the angle and goal, along with the distance to border and goal are used to fire the BVC. The speed cells layer during navigation has already calculated speed cells values, and they both border and speed cells and feed into the grid cells cell layers, and then it's firing the strands. Darker means the greater active firing or activities. So each representative, like the place cells layer, has a cluster of which is the smoothest, and the value determines in the place cells activities. So finally, we have the place cells activity is high, and oops, and as CM's the cognitive map segment is created between each place cells above the place cells threshold. Once the cognitive maps is created, and then we can get the shortest path from it. Okay, and then we have the some baseline simulation results. We can see that A is the what we have the head direction cells. We get all the this is for the first iterations, by the way. The PD, the preferred direction vectors far from the the obstacles, either near the start or near the goals, should be intuitive as the points they direct towards the target. And with local minima or like the actors appears to wander aimlessly. This is all about part of the random logic as the actors moves itself out of the local minima, avoiding obstacles and navigating itself towards the goal. And the place of the optimizations here maybe can increase the look ahead distance because we just set this the default as 1, but we can, based on different type of the map settings or scenarios, we can change to different settings. And B are the speed cells, as shown that like the darker orange here is the higher speed, and while lighter orange or the white indicates slow or no speed. It should be apparent that the locations where actors move in straight lines, yes, toward targets reach the highest speed. And C is visually the plot is the most abstract, to be honest. But with the dark blue squares representing the peak BVC border vector cells activities acting a repulsive force. These are cells which in the actors must avoid. And this shows that both grid cells, plate cells, and BVCs along obstacles boundaries. Grid cells activity is shown with the shade of green, where light green is low activities and dark green is high activities. And this is the final trajectories we have generated. And this figure showing like 1,500 iterations to navigate to the target at first iterations. Again, I just mentioned we can adjust like the exploration or look ahead distance to make it faster. And then we have the just mention if the two training iterations within 5%, so we break from the learning things. Okay, this means it's almost perfect for the final results. And then we have some basic comparison studies with other cognitive math models, like the compare with the vector and topological based navigation with cognitive mapping, the VTNCM. Here's the four scenarios. That's like we have several doors opening, and the true one is only door five is open. And in the tier two, it's all doors are open. And in the tier three, doors three and five are open. And tier four, only doors one and five are open. Uh, so this is more like a dynamic environment. And it's showing here like our result is much better than the VTNCM models. And the key takeaway from this comparison is that the GDCM can accommodate the static changes to an environment between iterations. This has profound implications to like the real world situations. For example, the GDCM can adjust depending on doors opening or closing, load closures, stored vehicles, or foreign debris over roadways such as the trees or large rocks. We have also compared with another algorithms is episodic memory-based self-organizing learning as EMSOL. There's another results over showing here. And we can see that from these tables, it is the EMCSOL is the shorter path from the true one. It is because just well, I can just mention like it's that it's because like we have a larger like not set very carefully about the look ahead distance, so we can have some more specifics for different type of locations. I mean, it's, environment settings. We can have better results shown here, and yes, this is the result what we're showing for the EMSOL. And the other is we have the better result after iterations. We have found a better look ahead distance. And also we have searching for different type of the benchmark experiments compared with some well-known studied past training models like the DLACO, the APA-CA, and MOFA. Our results most likely have the best results, talking about the path length, turning point, and smoothness in most cases. And also we have some discussions about our models. First, we'd like to talk about the model parameter sensitivities. Since we have the head directions cells, it not have the new activities. They don't have any parameters. They only just generate this as the vectors. And the others, like the boundary, the BVC, the speed cells, they have the parameters, and eventually they're just organizing to the place cells, and just like the neural activities to make sure which one is the best to for the robots to follow that path. And we can see that low place sales threshold activity activates the nearly every place sales that visited. So it's more like the generalized cognitive maps models. There's a large space for visited and stored in the memories. And then this is ideal when like we can just have a better, I mean, the less ages and nodes in the environment. But with the high PC threshold prevents many places cells from activating. And also we talk about the robustness and adaptabilities. We test the GDCMs under sensor noise and dynamic obstacle conditions. With moderate noise, the model remained accurate due to its layered redundancy, especially from boundary and grid cells. And in dynamic environment, the GDCM respond to unexpected obstacles with 86% successful replanning and only 1.8 average additional iterations. This demonstrates its potential for real-world and time-sensitive applications. So conclude what I just present in these seminars is the goal-directed cognitive map. GDCMs offer a novel bio-inspired models for robot navigations, and by integrating all known cognitive sales types and leveraging the Mammalian's navigation strategies. And GDCMs enables efficient purposeful movement in complex environments. And it advances both the computational neuroscience and robotics fields and lays a strong foundation for future biologically grounded AI navigation systems. Okay, thanks. That's all my presentations. Any questions?
Any question from audience? Any question? Okay, so let me have a question for Dr. Lei. For instance, now if you want to implement your model, which is really a excellent model, so onto the actual vehicle, right? So what kind of a challenge you have?
So yes, we definitely want to transform
Implement, yeah.
yes, implement that into the real robot, in the physical robot. Several we need to think about like how we have the sensor fusions integrate with the past learning models, and we can have some like control models to say okay how to have some adapt to the constraints of the physical the physical robots, right? Every robot they have their own constraints, and we can think about how we have the like also we can implement that into the multiple robots because it have the dynamic adaptabilities and it can be work for multiple robots to work together.
Okay, great.